Swayam Prabha. Digital India. Educated India.
So in the first session, you've gone through a bunch of open problems and see the good couple of questions out there and many more. So I'll be giving maybe two lectures, short ones. And in the first lecture, I'll try to complete the Rent division portion which we started yesterday, and we'll see what to do in the next lecture post-lunch. And okay, so I'll recall the model of Rent division again, and let's see, okay. So remember, Rent division entails having, let's say, n indivisible resources, in which in this particular case we can, let's say it n rooms, and we have a divisible resource which is money, and it entails us to divide the rent and allocate the rooms in those n friends or n agents such that no agent is envious of any other agent under that imposed rent, right? So I'll again formally write the definitions and model. So right now we are dealing the paradigm where we have indivisible resources along with a divisible resource. So once again, I'll emphasize on this particular point that in just when you have discrete resource allocation, which means you have just indivisible resource, envy freeness may not exist. A very trivial example is you have two agents and one single good whom they both value, let's say, positively. But as soon as you introduce some divisible resource into the system or into the economy, you can compensate that envy with the money you have at hand. And that's why you again have an existence of envy freeness in such economies. So you have n agents and you have n indivisible resource, which we'll call them as rooms, and some total rent needs to be matched, and we'll see about it. And then you need to, so an allocation sigma comma p, okay, let's say these are sets of agents, sets of rooms, and you have equal number of rooms and agents. Okay, so an allocation sigma comma p, where once again remember, sigma is a matching or a bijection from the set of agents to the set of rooms, telling you which particular agent will go or will reside in which particular room, and you have a price vector living in Rn space telling you, okay, these are the prices of n rooms I have imposed on the agents. Okay, so an allocation sigma comma p is said to be envy free. If something like this happens, and again I'll be denoting the utility functions they're deriving by this particular function. So you have a utility function for each agent A, for each room R, and yeah. So this particular function takes prices as input and outputs the utility of this agent A for this room at whatever price it is. Okay, so you have envy freeness if and only what happens is valuation, okay. Utility in agent A is deriving from the room he's been assigned to at price P of sigma A. So this utility must be at least his utility from any other room under the imposed rents P. Okay, so he goes around, he knows, okay, these are the prices fixed for these particular rooms, and this particular room is the room from which I derive the maximum utility. Okay, yeah. So this happens for all agents in your system, and again this happens for all rooms. Yeah, he must not be envious of any other agent and shouldn't be thinking, okay, I could have gotten this room at this particular price vector and would have been happier in terms of utility. Okay. So I hope this model again is clear and you all now remember what it is. Okay, so first question comes of existence. So can I before even talking about computing such an NV-free allocation sigma comma p, do I even know that such solutions exist? So existence is the first question naturally comes to our minds. And so there's a work by Alkan et al. In 1991 who showed that there always exists NV-free solutions, and by NV-free solution I mean that this tuple sigma comma p, NV-free solutions for any n given that the utility functions enjoy these three assumptions. Utility functions of each agent. Each agent is, number one, I'll write three assumptions and I'll tell you what they all mean. So they must be bounded as a function of p, because the argument this function is taking is a price vector p, price p. It should be monotonic and monotonically decreasing, and finally it should be continuous in p. Okay, so what do I mean by bounded? It shouldn't be the case that, okay, there's one particular agent in the system and he's thinking, okay, I just want to get this room at any price you post, billions, zillions, I'm ready to pay. This shouldn't be the case. Their valuation or their utility function should be bounded, and they should be rational enough that, okay, it's not like they're wanting or willing to pay zillions of money for some room. So this is what I mean by boundedness. Monotonic simply means for a fixed room, utility you're deriving from that particular room, let's say at $10, must be lesser than what you'll derive when its price is, let's say, $5, right? If you're paying higher rent for a fixed room, your utility must go down, right? And then finally, continuity is an assumption you again have, that these utility functions do not have they are well behaved in the terms of continuity. Okay. So this result of Alkan et al., which came in 1981, was again non-constructive. It was just an existential result, and this very general enough utility model. Like, you just need bounded. These are very natural assumptions you have when you want to model this, to have a model on this particular problem. Okay. And also, it would be a good exercise to again show that these three assumptions are necessary as well to show that there always exists an NV-free solution. In other terms, what I'm saying is, let's say you drop boundedness, you will be able to find counterexamples in which an NV-free solution may not exist. You drop monotonicity, you drop continuity, having, let's say, the other two, you'll always be able to come up with counterexamples. So these three particular assumptions are necessary and sufficient for guaranteeing NV-free solutions in our Renn division instances. Okay, so this came in 1991. This was a very well written paper and very strong result. They used bare minimum assumptions and proved existence. So we will obviously not go into the details of this particular result, and we'll move forward what happened, let's say, in the coming years. So in 1999, so in 1999 there is a researcher, Aragonés. She proved another remarkable result in this space, and she said, okay, we have existence for a very general utility model. Let me focus on some particular utility model and see that, okay, can I come up with polynomial time algorithms, or can I come up with some efficient algorithms to compute NV-freeness in the system? So So first of all, what she did was she came up with a correct, okay. So the utility model she was considering was quasi-linear, which we saw yesterday, quasi-linear utility model, by which I mean that this utility function is, let's say, at particular price x. This is a function which can be written as every agent has some base value VAR for this room R, and the utility is just defined as this base value minus the price she or he is paying for this particular room. So this is a quasi-linear utility model, and again, to see how does it look, it looks something like this. This is the utility of agent A for this room, and this is the price. And if she just gets to live in this particular room for free, the utility she'll derive is VAR, and therefore we also call this as a base value. So this is like the base value of agent A for room R. And if she is compelled to pay this particular amount, which is, let's say, VAR, her utility will be 0, because VAR minus the price, which is VAR, is 0. And from then on, it will be negative. Right? So this is a quasi-linear model, and note that the slope here is -1, as we saw yesterday. So in this restricted utility model, we already have existence for the general enough. This is a restriction of the bounded monotonic continuous utility models. So she gave a characterization . So she gave a characterization of the allocations which can possibly induce an NV-free allocation. So characterization of the assignments, let's say sigma, allocation is sigma comma p, the whole thing. Assignment sigma that can possibly induce an NV-free solution. And as we saw yesterday, this particular characterization, can someone recall what characterization which we saw yesterday? Yeah. Maximum weight perfect matching where? In the valuation graph, yeah, right? So give me an instance of Venn division. You have set of agents, you have set of rooms, and then you have this particular utility functions, where currently I'm assuming they're all quasi-linear. You consider a valuation graph, and remember, how did we construct it? Okay. So you have set of agents on one partition of this particular bipartite graph, and you have set of rooms on the other hand. And it's a complete bipartite graph to begin with. So you have like edges going from every agent to every room. So it's a complete bipartite graph, and with this we called as, I think, G of Q, as far as I remember, yeah. And the weights you have on an edge AR is nothing but the base value that particular agent has for the room R, right? So let's say this is agent A, this is some agent R. You have an edge going from A to R, and the weight you have is the base value VAR, right? So this was a valuation graph, and what we saw was if sigma comma, given this particular Venn division instance, if sigma comma p is an NV-free solution, then it better be, so the sigma over here better be a maximum weight perfect matching this particular valuation graph, the corresponding valuation graph of the Venn division instance Q. So this sigma must be a maximum weight perfect matching. In GQ. in the corresponding valuation graph. And so we also saw that in the proof only, if you will just go to the proof once, like go through the details, you'll also get this particular argument that let's say you have sigma comma p, which is NV free, and you have any pi, which is a maximum weight perfect matching. I'll say PM for perfect matching in the valuation graph. You can deduce that this particular pi coupled with this particular price vector once again becomes an NV-free solution for Q. So this was again for Q, the given N division instance. Okay, yeah. So yeah, this is the recap of what we did yesterday, and yeah. Any doubts on the model or the characterization in particular? Again, just to emphasize this characterization, like, okay, I have not written it formally, I wrote it formally yesterday, do refer it. So this particular characterization is a very strong one. It says that in a quasi-linear utility model, the assignment, the matching sigma must be a maximum weight perfect matching in the corresponding valuation graph. Okay. Do you have a question or someone, I think? Question, okay, I thought, okay. Yeah. So, okay, note that in particular, what is the power of this particular characterization? We are indeed able to decouple this sigma in P. So, our aim was to find the tuple sigma comma P, but strengthened by this particular characterization, we are able to decouple sigma and P. So I already know what sigma is, no matter what the price vector P is. I can separately find sigma and then working on finding the price vector P, right? I already know that sigma must be a maximum weight perfect matching in the graph GQ, right? So therefore this just directly again gives you a efficient algorithm for computing NV-free solutions in N division instances where you have quasi-linear utility model. Right? So what will be the algorithm? I'll again write a pseudocode and yeah. So input again is the N division instance. And note that I can also write this as just these VARs, because that completely defines the utility model, because we are in the quasi-linear setting. This is the input, and I need to output a sigma comma P such that it is NV free, or let's say an NV free solution sigma comma P. Okay. For the given instance Q, obviously. So what you do, the first step of the algorithm is to compute, to first of all construct the valuation graph and then compute a maximum weight perfect matching in the graph. And you have a bunch of, you can basically compute a maximum weight perfect matching in poly time, in particular via linear programming. So what you do is you compute a maximum weight perfect matching, anything. Like there can be a couple of maximum weight perfect matching, just compute any one of them. Perfect matching in the corresponding valuation graph GQ. And then you already know, let's say this is sigma, so you already know the assignment sigma. Then you just need to, the next step is to compute P, right? So what we do is we just write a linear program and let's see how we'll do. So, okay, I hope I have enough space, but okay. You maximize, there's no maximization, but yeah, let's say it's a vacuous maximization objective, but yeah, okay. The constraints are the one which we need to focus on. So you need to have NV freeness constraints, right? You need to decide your price vector such that you have NV freeness in the system. So you just need to write NV free constraints, and we'll see it turns out to be linear constraint once you know sigma. And in this particular model, we enjoy the liberty of knowing sigma because we have that powerful characterization at hand. Okay, so it's subject to the constraint that I'm writing the NV free constraint, so do note how am I writing. So I know that agent A is getting room sigma A. I already know that, right? I need to decide the price vector, and let's say this is P sigma A. Oh, so then let me have P here. Okay, P is the unknown variable here. Okay, so you have basically you have n variables here. P1, P2 till Pn. So this particular linear program will have n variables, which you need to compute. Okay, so what do I write over here? Like what would be the NV free constraint? Anyone but louder so that I can hear. Yes. Yeah, exactly. So it should be the case that utility this particular agent is deriving from any other room must be lesser than what he is getting from his particular room. Note that I know sigma, but I don't know the price vector P, right? You write this particular constraint for all agents and for all R. Fine. But here I can simplify this particular constraint by writing it like this because I know that we are working quasi-linear model, which is a simple case. Yeah. Again. Yeah, so this is my linear okay, so can someone tell me why is it a linear constraint? And yeah, why is it so by a linear constraint I mean that the variables you have a power of 1 only. They appear linearly in the constraint. So why are these constraints? Okay, first of all, okay, how many constraints do I have? For each agent I have how many constraints? N, right? And this happens for every agent. So in particular, I have n square constraints at hand. Okay. For every agent, I have I need to go through all rooms and I need to do this for every agent. So n into n. So why is that a linear constraint? Yeah, that I've already written, but okay, the observation is these are the so this is the variable in your program, right? And they are appearing linearly, like there's no power. And this particular thing you already know, right? These things. It's a constant you know. Since you know sigma, you also know VA of sigma A, right? So these are all linear constraints. So you do have linear n square constraint at hand. Okay. And so if you have a linear program, you can again obviously solve it efficiently. We know that linear programs resides in the polynomial time complexity class, right? Ellipsoid algorithm was the one to prove it. Okay, so yeah, that's it. That's the algorithm. You compute a max weight perfect matching, which can be done in polytime. So this step can be done in polytime, again via writing, let's say, a linear program, and this particular step can again be dealt via solving a linear program and again efficiently. So in total, this particular algorithm has a runtime of runtime which runs in polynomial steps of the input size, right? Okay, so the space where you have quasi-linear utilities is done, right? You already have a efficient algorithm at hand, right? Any doubt? Okay, sure. Okay. Well, oh, this is like there's no maximizing constraint, like there's no objective here. It's 0. Sorry, okay. This is 0, like 0, not O. Yeah. You don't need to maximize anything, you just need to come up with these price vector such that these constraints are satisfied. That's it. Yeah, exactly. There's no objective here. So is this particular algorithm clear? Any doubts? Okay. Yeah. Yeah. If this is clear, I'll move on to next part. So this would be a good time to ask any questions. Okay. Yeah. Okay. So I'd like to revisit the secretive setting, and for that, okay, so first of all, I'll just want to tell you a discrete theorem which is known as Hall's theorem. Yeah. Yeah. So Hall's theorem is a very well celebrated theorem in graph theory and has a lot of applications in various other branches. And it basically gives a characterization for, so given a bipartite graph, when you can say that, okay, there will always exist a perfect matching in that particular graph. So it just gives a characterization for the same. So yeah, it says that, okay, a bipartite graph, let's say G, so it has two bipartitions, V1 and V2, and there's bunch of edges going from V1 to V2 and not amongst V1 and not amongst V2, since it's a bipartite graph. So a bipartite graph will have a perfect matching. Okay, let me also assume that the size of V1 and V2 is exactly same. Yeah, let me assume it here. Okay, so a bipartite graph G will have a perfect matching if and only if one particular condition is met. If that is there, you are guaranteed to say that, yeah, this particular graph will have a perfect matching. So that okay, so have you ever heard of Hall's theorem before though? Yeah, okay, yeah. So yeah, let me write the condition and then I'll explain you what it means. So it says that for every subset S of this particular V1, okay, so you have V1 and you have V2, and you take any particular subset S and then you check the neighborhood set of it. Okay, I need to define bunch of stuff. Okay, so gamma of S, what is it? This is just okay, let me be. So let's say S is a subset of V1. Gamma of S is a subset of V2 and it is defined as those vertices in V2 such that you have an edge going from V1 to V2 where V1 is in S. Okay, let me just say that, okay, let's have a running example. So let's say this is your V1 and this is your V2. Let's say this is the graph I have at hand. Let's say this is a bipartite graph given to me, G of V1, V2, and these are the bunch of edges I've listed. Okay. So it just says that, pick any subset S of V1 and then just see the neighborhood set of this particular set, by which I mean that, okay, just check where the vertices of S gets connected to which vertices of V2. So in this particular case, this is the neighborhood set of S, right? I hope the definition of neighborhood set is clear, right? It just says that pick these vertices in S and see to which vertices in V2 they are connected. And that particular set is the gamma of S or the neighborhood set of S. Okay. Yeah. So can someone tell me, let's say this is S dash, what is the gamma of S dash? No. So yeah. So what is the gamma of S here? S dash? Yeah. What is gamma of S dash in this particular bipartite graph? Yeah, last two edges, right? This is gamma of S dash. Okay. Okay. So I hope the once we have the definition of neighborhood set, this is also known as neighborhood set of S. So okay, so the Hall's theorem says that a given bipartite graph will always admit a perfect matching if and only if you have this particular condition, which is also known as Hall's condition. It says that take any subset S of V1, you must have, for every subset S of V1, we have the cardinality of S. Okay, by cardinality I mean the number of vertices in this particular set must be at most the number of vertices you have in the neighborhood set. If this is true, you know that a perfect matching must exist. Okay. Yeah. So can someone, okay, let us absorb the Hall's condition first. It just says that pick any subset of V1. If you have this particular property that the neighborhood set of this particular subset has at least as many vertices of the set S you considered, you'll always be guaranteed to have a perfect matching in the given bipartite graph. Okay, so in this particular example, can someone tell me, do we have a perfect matching? No, right? Why? What is the witness set S here? Second set. So what do you mean by second set? Okay, so this S only, right? So for this particular case, gamma S is, the cardinality of gamma S is strictly less than the cardinality of S, right? So even if you want to create a perfect matching, okay, so I give this particular vertex, I match this particular vertex to this particular vertex, where does this particular guy go? He doesn't have any other edge, right? That's more or less the intuition as well behind the Hall's condition. Yeah. So is Hall's theorem clear to everyone? Okay. So, okay, why am I defining Hall's theorem? I just want to give you a graphical representation of what do you mean, when do we say that we have that secretive fair allocation? What does it translate when you see it in a graphical setting? Okay. So, let me just recall the secretive setting. So, okay, so given, let's say, a Renn division instance, or given any fair division instance in cake cutting, indivisible, divisible, anything. So let me write fair division only. Okay, so given fair division instance, I say that an allocation A is secretive fair, which can be secretive NV free, secretive proportional, secretive epsilon NV free, but yeah, secretive fair, whatever fairness notion you want to have it here. So when do I say that it's secret? Okay, so remember you have n agents in the system, but only n minus 1 of them submit their valuation or utility functions to you, and the nth guy is a secretive one, and by which I mean that I do not really know anything, I don't have any information about the valuation function of that particular secretive nth agent. So an allocation is said to be secretive fair if what happens? Yeah, it's a very natural definition. It says that, okay, if for every choice, remember, see, once the allocation is done, a secretive agent comes in, pick any bundle he wants and goes away, right? So he can basically choose any bundle. So for every choice AK, so for every choice of secretive agent, you must be able to adjust the remaining n-1 agents in the remaining n-1 bundles such that that fairness notion is still maintained, right? Or you achieve the fairness notion. So for every choice AK, there exists a bijection. So there exists a bijection. Can someone recall what the bijection would be? Going from where to where? Bijection is a 1-to-1 onto function, right? So it should go from where to where. So bijection pi k. So it should go from where? Like, go from where? Yeah, just repeat whatever you said. I need to allocate the remaining n-1 agents, right, to somewhere. So it should go from n-1, which is the remaining n-1 agents, to where? To where? Yeah, n-k, right? n-k. Or by which I mean that you have this bundle from where this particular set is being removed, right? And that's what n-k also represents. So you have, so for every choice AK of the secretive agent, there exists a bijection function pi k such that the valuation function of A for whatever bundle he is getting under this bijection map pi k, this must be at least whatever, so this must be, oh okay, sorry. So valuation of this particular agent he is getting from the bundle pi k of A, this must be at least what he is getting from any other bundle, right? So any other bundle agent. So this must happen for all agents in the first, so all first n-1 agents, and for all bundles, right? Okay. So this once again, for every choice that secretive agent makes, let's say it is AK, he comes and picks the bundle AK, you are able to accommodate the remaining n-1 agents in a fair manner, right? So remember, for proportionality you had, we gave a moving knife procedure and it achieved, so we were able to give a polynomial time algorithm which achieves secretive proportionality, and in that particular proof we saw this particular backup scheme. Backup scheme, so scheme I think I denoted it by sigma, and so sigma I was greater than, or let me have sigma A because I've been denoting by A. So what was happening was the agents were coming and claiming their bundle, right? So this particular procedure was, so we ran moving knife procedure on n-1 agents but with a threshold of 1 by n, right? So first agent came and picked up, reserved a bundle or reserved a piece of cake P1, P2 and so on. So there were like n-1 cuts made and therefore an n partition was created, and this was a leftover piece. Yeah. So if you consider this particular graph, so you have n-1 agents here and you have n bundles or n pieces of cake currently here. So this particular graph, how do you describe the edges? So this agent 1 draws, so remember VA of PA was at least 1 by n, and there exists some particular B which was ahead of A in the indexing, such that VA of PB was again at least 1 by n. So he had some particular choice ahead of his particular reserved piece PA. So I know that, so I'll draw these edges. So going from, so every agent A draws an edge to his reserve piece PA, or basically he draws an edge to a bundle from which he is able to achieve the fair share. In this particular case, proportionality, right? So every agent will draw, so this is, let's say, A1, this is A2 going to PA2 and so on. But what is also happening in this particular case is every agent A also draws an edge somewhere ahead of it, right? He has a backup scheme, which was this sigma of A, right? So if you consider this particular, let's say something like this is there. Let's say this is your instance, this is the graph you construct. So in this particular instance, what you can show is you have, okay, remember once again, whenever a secretive agent comes in, he picks one particular piece, this piece goes away, and the remaining, so now the graph which is remained, which we get after removing this particular piece, is on n-1 agents here and n-1 bundles on the right hand side, right? Currently there were n bundles, but one is gone. So you have like n-1 agents, and you have n-1 remaining bundles or piece of cake. So now it's a balanced graph. And now you basically want that after removal of this particular piece, you are still able to come up with a matching pi k, right? So for that, if I just have a Halls-like condition for this particular graph, I am done, right? Because if I have Hall's condition here as well, I know that there will exist a perfect matching, right? So what I want is for this particular graph to, so let me denote this particular graph by, let's say, f of the given instance Q.